Glad to see on a I guess it's relatively warm compared to the days we've had in the past. Night here at IIT, such a really good audience. School, everyone, it's good to be here. My name is Alan Charisse. I am the Director Emeritus of Argonne National Laboratory. That was my previous day job. And I am the President of the Chicago Council on Science and Technology. That is the organization sponsoring the event this evening. We are a relatively new organization, and our mission is to raise the awareness of the importance of science and technology among our citizenry. In the current age, that is indeed an important issue for the nation, and that is an issue that we are geared to deal with by having meetings such as this, where we talk about topical topics on science and technology that are of interest or should be of interest to our citizenry. You should have with you a brochure that has within it an audience participation card. Appreciate it if you would fill that out. And also, in order to develop this organization the way we think it should be, there is a sign-up ability within that card. So those of you who are interested in continuing to attend events such as this, please take the opportunity to sign up. The C2ST is composed of almost all of the scientific and technical organizations within Chicago, universities, national laboratories, museums, industries. And I'm glad to see here tonight board members. John Anderson, if you will raise your hand. John is the president of IIT and the host of, in addition to the meeting, the host of C2ST, the organization itself. We thank you for that. Pat, wife. And I will introduce our next board member, Paul Knappenberg, who is the president of the Adler Planetarium. And Paul and a very small group of senior administrators in the Chicago area formed this organization several years ago. So Paul has a vested interest in it, as do I. Paul Knappenberg will introduce the speakers and serve as the moderator for the evening. Paul.
Well, thank you, Alan, and welcome to everyone. And I want to add my word of thanks to John Anderson for being our host this evening in this wonderful facility. If you're not members of C2ST, I encourage you to think about becoming a member and helping us spread good information around Chicago and the surrounding areas about science, technology, engineering. And our goal, as Alan said, is to help people better understand the various fields of science, technology, engineering, but especially as those topics become important in making decisions about public policy issues, so that you can be in touch with elected officials, or if you are an elected official, be more knowledgeable about the science behind a lot of the issues that face the public today. This evening's program, The Moon, is, I was also supposed to, and I'll do that right now, mention the next program that C2ST has coming up, and that will be on February the 17th, and it's called Cyber Security, and it will be held over in the Hughes Auditorium at Northwestern University. And the two speakers that evening will be Jason DeHaan from the city of Chicago and Mike Swarek from Argonne National Laboratory. So mark February the 17th on your calendar. Tonight's program on the Moon is being co-sponsored by two institutions, the NASA Lunar Science Institute and KV-265. NASA Lunar Science Institute supplements and extends NASA's lunar research programs. NLSI is managed by the NASA Ames Research Center out in California. But the teams of the Lunar Science Institute are dispersed across the country. And they work together to lead the agency's research activities related to lunar exploration. KV-265 is a nonprofit organization whose mission is the communication of science through art to the general public, to school children, and educational institutions around the world. KV-265 promotes the creation of multidisciplinary works that bridge the worlds of art and science to increase the understanding and appreciation of these great human endeavors and to expose them to ever greater audiences around the world. So we thank both of those co-sponsors this evening. I'll now introduce the two panelists who will, in turn, share with you some information about the Moon. And our first speaker this evening will be Dr. Gaza Duke. Gaza's on my far left, your right. Gaza is Director of Astronomy at the Adler Planetarium and is a Senior Research Associate at the University of Chicago. He received his undergraduate degrees in physics and math from Brown University and his doctorate in physics from the University of Chicago. Dr. Duke's research work is outlined for you in your program this evening, so I won't go into all of the many areas that he has dabbled in his research. But I do want to just take a minute or two and let you know of his education and outreach interest. He's worked very closely with our educators at the planetarium to develop exhibits and sky shows, educational programs. He's worked with the media on interpreting and explaining astronomical events that have occurred. And right now, one of the most exciting things that he's involved with is a program that gets kids and adults hands-on experience in doing space science using high-altitude balloons. And they design and build payloads and launch these things up to about 100,000 feet or so, literally the edge of space, and collect data on the way up, and then a parachute lowers the thing gently into a soybean field somewhere in southern Illinois, or a tree that's growing on the edge of that field, and then the team goes and recovers it. And so if anybody has got any interest in that sort of exciting kind of science, see Gaza afterwards. Dr. Jose Francisco Salgado is also an astronomer at the Adler Planetarium and a visual artist. And he is executive director of the KV-265 group that I mentioned earlier. He is formally trained in physics, getting an undergraduate degree at University of Puerto Rico, and then his PhD at the University of Michigan in astronomy. Again, his background is laid out for you in the program book tonight, and he's been involved in lots of interesting things, Spanish language, educational programs in astronomy. His news program actually was nominated for an Emmy award. I think, to me, one of the most exciting things are these films that he's been producing that go along with symphonic works. So Gustav Holst's The Planets, and Mazursky's pictures at an exhibition. And he's taken these films and has performed with live performances of symphony orchestras around the world with these films as a background. He's done that here in Chicago a couple times, including once at Millennium Park in the Pritzker Pavilion stage. If any of you had the opportunity to see that, I'm sure you appreciate the quality of the work that goes into that. His work was selected by UNESCO to be featured during the International Year of Astronomy. And so when they kicked that off at their headquarters in Paris in early 2009, his work was featured there. And it's now been shown in 13 different countries around the world, 50 different venues. And I think at this point, I should mention that he's currently working with Tom Bailey, who was formerly with the British pop group, the Thompson Twins, and they're working together on a musical and art piece. And I think Tom is coming over to visit us next May, I believe.
May 19th.
May 19th.
Public event.
Out at the Adler Planetarium, so write that on your calendar too. Okay, so at this point, I'll ask Gaza Duke to come up and tell you a little bit about what he knows about the moon. Thank you.
So, the moon has played a role in life and society for, well, I was going to say millennia. It's probably much greater than that. It's for billions of years, really, in our biology, the circadian rhythms, so to speak. In more recent times, in religion, or sort of a light source, something that sort of sets our calendar, timekeeping, in navigation, and just in an inordinate number of ways, the moon shows up. It's completely recognizable. Everybody knows what the crescent means when you see it. It's ubiquitous. So I just selected a few things to sort of illustrate this, things that sort of were a little bit intriguing to me when I first came upon them. For example, here we have some corals, and corals, not exactly the smartest things in the world, even brain corals, but somehow they know what the moon is doing. And once per year, 8 evenings after the August full moon, you have a spawning, coordinated to within minutes. So somehow these corals are very deeply connected with the moon, and the exact mechanism is still a bit of a mystery. All right, so religion, there have been moon gods and moon goddesses forever. I just randomly selected two. Diana, god of the moon, and hunting is very, very familiar to all of us. Perhaps a little less familiar is the Egyptian moon god Aya. You can sort of see right up here the crescent. That's very classical. Crescent moon just before the new moon, and then the full moon inside. So the moon has been with us in our religion forever. So a little factoid that I didn't appreciate until this was pointed out to me by my wife is that, in Greek literature, you can also find the moon. Parties used to be scheduled by the moon. You got to get home after the party. Maybe you're weaving a little bit as you drive those carriages. You want a lot of light so you can get back. So, if you want to schedule a party, schedule during the moon and make sure you get in early so that, everybody else's calendars aren't full. So, harvesting by the light of the moon. We even do that in the modern day. And then navigation. You measure the altitude of the moon above the horizon, and then the sun's altitude above the horizon. If you know the time as well, then you can fix your exact location to one of 2 points. Okay, so it's not perfect, but if you don't know whether you're in the North Atlantic or South Atlantic, it's probably a little too late anyway. So, and there's this sort of lunar and celestial navigation was very, very important. And of course, nowadays we have GPS, and of course we still may make the mistake, but hopefully not. So, in addition to the sort of the social and life and biology sort of connections, the moon has also served as a keystone in our developing scientific consciousness. It's sort of right there in our face. And you can't help but notice things are changing. It orients us towards the sky. And so I just sort of have a list of things here. The lunar orbit and phases, of course, and sort of the timekeeping that goes with that. The phenomenon of lunar eclipses is important in our understanding. You can learn about the shape of the Earth from looking at the moon. I'll mention that in a little bit. The imperfection of the celestial spheres in Galileo, and then the developing consciousness of the moon as another world. So we'll start over here, okay? And so here are the phases of the moon. We've got the moon moving around, and as the moon moves around, you see different phases. And so, you know, it's very geometrical, very direct sort of interpretation, and this wasn't, there were many, many myths to explain the changing of the moon and the shape of the moon. But eventually, you know, during the Greek period, ancient Greek period, this was begun to be appreciated. This is merely a geometrical effect. You don't have a wolf eating the moon slowly and then disgorging it later. And so it's sort of the beginning of this sort of geometric scientific consciousness. Here's just a lovely picture of these phases as they move over. One of my pet peeves in children's books is when they present the moon and it's got this impossible phase of sort of a bite taken out of it like this or something, which doesn't happen. You know, the phases all go from the top to the bottom, or, you know, they're these graceful arcs. The other one is, of course, that it's always night when the moon is up. And of course, half the time when the moon is up, it's daytime. And, but it's really drilled in. I found my own children, who you'd think as a children of an astronomer would know about the moon, saying, the moon's visible during the day, really? But, so, all right. So let's slow that down a little bit. So after you notice the phases of the moon, you also, oops, I think I'm going backwards, actually. You notice something interesting, and that's basically the moon always shows the same face to us. Why is that? What's going on there? Why does the moon always show the same face? You can actually see that actually the size of the moon changes a little bit over time, and exactly what face, it's sort of wobbling a little, but mostly the same face is being shown at all times. So, what's going on here? Well, the moon is in synchronous orbit, and as it moves around, so this is sort of the non-synchronous. If the moon didn't rotate, then, you know, you can see these dots. The different dots are visible at different times. The red dot when it's sort of new moon, and the blue dot when it's full moon. That would be, so the fact that we see the same face proves the moon rotates at the same time 1 month as it takes to go around the sun. And that was another one of the sort of people began to appreciate and understand that. Lunar eclipses, sort of the beginning of precision astronomy, to understand the eclipse cycles and why you have eclipses and when they occur and predict them so that you're not startled by them. It takes a greater, deeper understanding. You have to have a reasonably good grasp of math, at least sort of the Babylonian level. And fundamentally, it's just an issue of the shadow of the Earth. You've got the Earth here casting a shadow. You've got the darker part of the shadow, the lighter part, the umbra and the penumbra. And when an eclipse occurs is the only time you get these non-sort of crescent sort of things. The shape is different, but it's always this sort of, the curve has a smaller curvature. But what's interesting about this is from the eclipses, you can actually tell a lot, not just about the moon, but about the Earth too. If you look, you can see that these edges here are curved. That's the shape of the Earth. If you put all of these shadows, these moons in the correct position, you'd see that they trace out, the edges traced out a circle, about 3 times as large as the moon. And the Earth is actually 4 times as large as the moon, but the shadow tapers down. It's a tapering cone because the sun has some angular extent in our sky. So you have the shadow, and from that you can figure out the size and the shape of the Earth. And then if you know the actual size of the Earth, however many stadia, as the Greeks calculated, then you can figure out the size of the moon. We're beginning to understand the moon from this as an object that's sort of more than just something painted on the sky. And that really took a leap when Galileo first turned a telescope on the moon and began to see that there were mountains, shapes, craters, pits in the moon. It wasn't a perfect object. It wasn't this perfect celestial sphere out there. There's just lovely pictures. And of course, we have even better pictures now. And the moon is far from a perfect object. It's got scarps and rills and flat areas and mountainous areas, craters galore. So we really have begun seeing the moon as a different world. It's no longer just an object up there. It's a true world. And now that we've actually gone to the moon, that's absolutely the case. It's unescapable. If you've been there, if you've seen it, then and people have walked, that this is a world just much like the Earth, except, well, as I'll talk a bit later, very different in its details. These lovely panoramas are a wonderful legacy of the Apollo program. There we go. So the moon sort of had more to tell us. One of those things is the tides. This is sort of a rather extreme case of tides. This is, I think, something on the order of 8-meter tide. Hope I don't live anywhere where it's quite that high. I can imagine it does a lot of damage rushing in and out. But why does the water go back and forth? If you look at the timing, you can tell that it has something to do with the moon. You've got these high tides when you've got a new or a full moon. You've got these lower tides when you've got the quarter moons. And so people knew that there was a connection, and so there must be some connection. But it wasn't until later that we realized that it was due to the gravity of the moon pulling and sort of making this oblong. The Earth can't really move much, but the water can, and so the water provides this bulge, and then the Earth turns underneath it. And the person who sort of figured this out and made that connection between the moon and gravity was good old Sir Isaac Newton, nominated as what was the Time Person of the Millennium or something like that. Watching the apple fall, at least so the story goes, and thinking about the gravity acting on the apple, and did the gravity act on the moon too? And then sort of getting this conception of orbits as the moon progresses around the Earth. It's trying to fall towards the Earth, but it keeps missing the Earth. And so this is really the beginning of astrophysics. It's when we said physics has something to tell us about the other worlds, something beyond the Earth. It's really sort of the beginning of taking laws that were sort of understood on Earth and saying, wait, do they actually apply somewhere else? And together with this idea that the moon was a world, you really now, it's the sort of universe has come to us, and we're ready to go to the universe. All right, so our modern understanding of the moon, from these humble beginnings, it's been a lot of work. We now know a lot about the physical parameters of the moon, the fact that it doesn't have an atmosphere that makes it very different, and sort of a part of the whole big story about the moon is the craters. The craters are the most obvious thing, and they sort of are what have really shaped the history of the moon. So very first, I'll talk a little bit about the physical parameters of the moon. Here's the correct size relationship of the moon and the Earth. It's also sort of the correct darkness. The moon is actually a very dark object. It has a very low albedo. The astronauts who went to the moon, the Apollo astronauts, were very surprised when they looked at the moon dust, and it was like ashes on their suit. But it looks so bright because there's nothing to compare it against in the dark of night. But it's actually quite dark. It's also pretty small, about 1/4 the size of the Earth. You'd expect that it would weigh about 1/60th or so of as much as the Earth. It actually weighs less. It weighs 1/81st roughly, of the mass of the Earth. And that begins to tell you that the density is less, and that begins to tell you that the moon is not quite like the Earth. It's not quite just a body like the Earth, and I'll get back to that later. That's your first clue about how the moon was formed. All right, so the moon doesn't have an atmosphere, and you can see that very readily when you have occultations. Here's Venus, just about to disappear behind the edge of the moon, the limb of the moon. And as it moves, if there was an atmosphere, you'd expect to see sort of some dimming or reddening right as it passes through, just like sort of a sunset on the Earth. But you see nothing of the sort. The Earth has a thick atmosphere. The moon essentially has no atmosphere. You don't see any clouds or anything like that. And you don't even see evidence of tenuous cloud-free atmosphere here. A really lovely example of this is this grazing occultation of Saturn with part of the moon. Just lovely, and it's absolutely unchanged from here to here, illustrating that the light rays just go straight by and are totally unaffected. So that already tells you that the moon is not going to be a very hospitable place for Earthlings in any event. So you take a look at the sort of large-scale structure of the moon, and you think, you look, and it's just, it's studded and dotted with all these craters, these holes, these sort of circular depressions on the moon, various differing colors filling them. What are these? And for the longest time, people didn't really know. They were just circular holes. And then people sort of started thinking that they might be volcanoes, because that was sort of the closest analog on Earth. But in the 1800s, late 1800s, it began to be realized that these might not be so. But it wasn't really until the early 20th century that sort of things began to firm up that these were impact craters. So an impact crater is essentially just a very high-speed object, any bit of junk floating around in space, crashes into the surface and sort of almost burrows in, and then the shock waves and the energy sends out a blast, a shock wave, and that excavates. The whole stuff is thrown out, and then there's sometimes a rebound in the center. This is for a complex, large crater. The central peak peaks up, and you've got these the ejecta blanket, all this stuff that gets thrown out on the side. Usually, the impacting object is fairly small. It's moving very fast, tens of kilometers per second, so there's plenty of energy to make a hole much larger. We're not talking about just sort of making a small dent in the surface. It's a very large, high-energy event. A perfect example, I believe this is an LRO image. It's a simple crater. There's no central peak in there. Here you have a slightly more complex one of terracing as the sides have sort of fallen back into the crater and the central peak, and then you can see the sort of rays of ejecta, stuff that's thrown out. In some of the larger craters, this stuff can be thrown out essentially over the entire circumference of the moon. And in fact, later on, after the Q&A session, some of this material actually gets thrown so violently it leaves the moon entirely. And there are lunar meteorites, pieces of the moon that have fallen to the Earth. And we actually have a sample of one of them here, which you're welcome to take a look at, touch carefully. So by the end of the night, you can say that you've touched the moon. All right, so a real new era in our understanding of the moon came during the Apollo missions. That was when we had the chance to actually go on a scouting mission and get an on-the-ground truthing. It's one thing to look at sign from a distance. It's totally another thing to actually get there and get your hands dirty and bang around with your hammers and take back samples. We have some lunar samples from the lunar meteorites, but we didn't necessarily know those were lunar samples until after Apollo, when we could compare the isotopes and the chemistry of them. And we got an appreciation for the whole moon. We had sort of gotten a good idea of what was happening on the moon, but we had only seen half of it until Apollo and the precursor missions. For example, the Soviet missions, the surveyor missions, and so forth that were scouting out for Apollo. got a much better understanding of the nature of the mare and the highlands, which I'll talk about in a moment, and then also the violent origins of the moon, how the moon actually got started. All right, so here we go. This is the near side, the familiar side, all these big dark blotches here. And as NASA calls it, the right side. That's on your right-hand side as you look at the moon. The far side, not to be confused with the cartoon. And the left side. And if you look at this, it's really sort of, oops, all right, let's make sure. The far side looks nothing like the front side. None of these big blotches with a sole exception here. And then you can also see something that you only see a little bit on the near side. It's this huge crater, this basin here, the Atkins Basin, that's really one of the most violent impacts on the moon. Okay. And finally, you begin to get an appreciation of the whole thing. It's a topographic map. There's these big differences. Here's that big crater on the far side of the moon, the Atkins Basin. It's larger than any of the other ones. It's one of the largest impact structures we know of in the solar system. So here we have the moon as a world, as brought to us by the missions that actually visited the whole thing. You begin to see the far side coming up over here. Some very dark craters over here. These are, as I'll mention in a moment, lava-filled. So you can sort of already see there's two different types of terrain. There's the sort of whitish, light-colored areas, and then these dark-colored. If you looked at the previous slide, you'd see that, so let me go there. These guys are low, and these guys are high. You can see that in the topographic map, especially in the far side over here. Those are the highlands and the lowlands. Okay? And a little zoom in, you can see that they look very different. It's very smooth here, very rough here. What happened with these is these were late large impacts where it gouged an area, cracked the crust of the moon deep enough so that lava came welling up and filled these with whole seas worth of lava. The few craters you see on top are ones that came afterwards. And you can see these sort of structures, these linear structures here from the lava flows. There, and you can see these are sort of basalt plains, these areas. So they're evidence of volcanic action on the moon. So how did the moon form? Apollo helped tell us this. There used to be three different ideas. Capture, which the idea that it came from somewhere else and just came by and got captured by the Earth. This is actually dynamically very difficult. Objects don't just slow down in space. They have to have something stopping them. And it's difficult to imagine how that could happen. And then the moon and the Earth, now that after we got Apollo materials back, are very similar. They're not very different at all. And so why would something that's formed in a different part of the solar system be so similar? Co-formation, did they form together at the same place? Are they sort of a double planet? Then there are chemical differences, and so why are there differences? In particular, one of the big differences is there aren't very many volatile elements on the moon, things that sort of melt easily. Most of the stuff that the moon is made of is very refractory. They're sort of things like silicon and titanium and things that don't melt at low temperatures. And it was sort of puzzling. And the solution to this is the giant impact theory, which has a lot of support now. But we couldn't have really, without actually getting rocks back from the Apollo missions, we wouldn't have really had the chemical signatures for this. So this is the basic theory. You get the proto-Earth almost entirely formed, and then some other planet very rudely decides to crash into it, about the size of Mars, half the size of the Earth or something like that. And it throws off a portion of the mantle of the Earth. And in the heat of the collision, almost all the volatiles are vaporized and escape to space. What then condenses out of this cloud that's circling the Earth is the moon. And it used to be much, much closer, and then it migrates away. So it's almost too fantastical to be believed, but it turns out it actually was not that uncommon. We've got evidence of other giant impacts. Pluto has a large moon Charon, which probably formed from a giant impact. Mars has a whole half hemisphere, which looks like it was almost stripped off of a giant impact. Mercury has this huge crater on it that was very close. And you can go on with evidence that giant impacts like that were common. No one, as far as I know, has ever given a name to that planet that hit the Earth. But it was a planet-sized object, so it probably should have a name. All right, so, but the major picture that came out of the Apollo missions was that the moon is an almost dead world. It doesn't have any plate tectonics, nothing is sort of stirring up the surface. So all of the features you see are very, very old. There's no atmosphere, there's no erosion. It's a pretty much unchanging landscape. So this brings up the question, why might we even want to go back? Why bother? Dead world, Okay, been there, done that. Got to have some justification. The constellation program was sort of, I forget, Apollo on steroids, I think was the description. Apollo Redux. Why would we want to go back? Well, we think that the Apollo missions, we visited the moon, right? Well, that's true, but we only sort of saw a small fraction of the moon. In fact, if you look, the relative locations of Apollo superimposed on a map of the United States, this is the area we explored. This is the size of the moon. So we really sort of looked at only a small portion of the moon. The whole backside of the moon has been unexplored. Nobody felt quite confident to send a probe to the far side and maybe lose radio contact with it. So there's a lot to be learned. We wouldn't say that we understood America if we'd never crossed the Mississippi, right? So here we go. It's the sort of the vision of the Altair lander, bigger than the Eagle, I guess. And human and on-the-ground exploration is still the most effective way of understanding a world. There's nothing that beats just getting there and doing stuff. And robots are very flexible, but they're not as flexible as humans. So NASA's vision, which is currently on hold as budget woes are worked out. And here we go. Riding off into the sunset. There we go. Why go back? Well, there's a lot of mysteries still to learn. We haven't explored most of the moon. But then also, the moon is the key to space. It's got location. They say in real estate, location, location, location. Right? Well, that's the moon. It's not deep in a gravity well. Here on the Earth, we're 11 kilometers per second deep in a gravity well. It's difficult to get out. Not to mention, you've got this atmosphere all around you, keeping you from getting out. If you want to build anything in space, it doesn't make sense to bring things from the Earth. It makes sense to bring things from the moon. You've got resources, water, sunlight, low-grade ores to work on. And then for exploring the universe, you've got a radio-quiet side as just one example of many things that you can do on the moon. This is not a recent thing. This is a nice vintage painting from NASA with this mass driver. So you get your materials here, you process them, and then you shoot them off in this mass driver, a kilometer per second, which is only a tenth the speed you need on Earth, and it's off. It'll get flung off the moon forever. And then you can catch it in space and do whatever you want with it. So looking for water at the south pole of the moon. It's very cold in selected craters in the south pole of the moon because you get almost no sunlight. And so you get a place where water vapor traps itself over billions of years. Not a lot of water vapor from comets colliding with the moon, but every time a comet collides, you get a little bit of water vapor, and it's going to sort of float around the moon until it finds one of these cold traps. It either escapes from the moon or it freezes into a cold trap. And so there may be millions of metric tons worth of water in these cold traps on the south side of the moon. You've got low-grade ores. So here we have sort of a zoom in, the Hubble imagery and LRO imagery, sort of looking and the altimetry mapping. You can sort of start selecting good sites that you might want to do some mining in right here. Here you can sort of see these sort of mountainous regions here. And then, but you don't just have to have a mule and a pickaxe these days, you can actually know where the ores you want are. This is iron by weight. That's the function position. That's the front side. That's the far side. And then this is titanium. So you can just go to right to where you want. These are from the Prospector, aptly named mission that was looking for resources. Another side advantage of doing manufacturing on the moon is that pollution isn't nearly as much of an issue because there's no water or atmosphere or something to pollute. It's not going to go anywhere. Sunlight, you need power if you want to do anything on the moon. Well, there's some beautiful places where solar power is fantastic because you've got 100% sunlight. This is a map of how much sunlight these places get as what percentage of the time they have sunlight. Right on these crater rims on the South Pole, this is the South Polar region, you just get continuous sunlight because you never turn away from the sun. Of course, a mile away, you're down in the middle of the crater and you never get sunlight. Some of these are the coldest places known yet in the solar system. All right. And then you've got a radio quiet area. Build big radio telescopes and so forth. You don't have any interference from the Earth. So you could learn a lot about the rest of this universe. So the moon in our future. The moon has a lot of promise. There's a lot of things we could do down the line. But it's a really harsh place. The temperature extremes, hundreds of degrees variations. There's the vacuum to deal with, which can also be a positive. There's radiation, a lot of dust, and the dust is very sharp and gritty dust. So we have to learn to work and eventually live there to make that promise happen. And there are many things still to be explained. What is the role of volcanism? What happened when the moon was still completely molten as it cooled? Is the moon still active? There are some indications the moon is still doing things. It's not completely dead. What lies in those dark craters in the moon's south pole? Those are sort of been deep freezes for the past 4 billion years. There could be some interesting stuff in there. So I hope I've given you a little bit of a taste of the science of the moon and early cultural aspects of the moon. And so that concludes my portion of this. I'll hand things over to Jose, who will tell you a little about it.
So now the question is, how do we turn all of that into art? And for that, I will basically make a film that will be premiered at the end of the year with the Chicago Sinfonietta here in the city. And the music, it's going to be Daphnis and Chloe by Ravel. So there's so much imagery, right? So basically what I want to do is show you a couple of things that I have in mind. I literally started production recently and have been doing a lot of research, not only for the talk. Actually, just preparing this talk with Gaza was a lot of good work research work for not only for the talk but for the film as well. So the idea is to present the film projected on a very, very large screen. Here we see it on a 45-foot wide screen in Millennium Park. This was the planets in 2008. And then we take this around the world. This was also the planets in Taipei, just to give you a taste of how the experience. What the experience is about. And the idea, the mission is that many, particularly concert goers, they go because of the music, but then they get exposed to all this imagery that, many people haven't seen before. And the idea is to inspire them to learn more about science on their own. Then it's up to them to actually go to a science museum or watch a documentary on TV or read a book, but at least they get exposed. And of course, these events get accompanied by lectures just like this one, where we can talk more about the imagery. So of course, the moon has been the inspiration, or has played a important the role of important elements in many paintings. So here I'm just showing a few, just to stress basically that the film, it's not only about the scientific aspects of the moon, because I think it would be a little bit too dry just to show, image after image of just the surface of the moon, but to show its role in culture and in art, right, as an inspiration for art. Of course, Starry Night by Van Gogh has the moon as an element. And then, of course, in artwork, this is, the 1815 staging of the Magic Flute by Mozart. And we see, the Queen of the Night standing on a crescent-shaped moon. Okay, and then, of course, so paintings, right, art, historical documents, that's another thing. And like I said, I wanted to show you, so many materials, but that could be a talk on its own. Historical documents that could be from pop culture, from scientific as well, and then of course photography. Photography, as both as an art form and as well as a scientific tool, and that's why at KV265 we're developing these programs around photography, because photography is something that it's right there at the intersection between science and art. It can be used for both. And the asterisk is because I'm showing all these NASA photographs except for the first one, which is actually by the Soviets. So this is from 1959, the first image of the far side of the moon by Luna 3 in a stamp commemorating that event. So what I'm showing you here is a series of first pictures. So the first picture of the far side, first soft landing on the moon, 1966, and so this is, the mission Surveyor 1 was the one that, that demonstrated that this could be done and that, we could visit the moon afterwards. First photograph of Earth taken from the vicinity of the moon, and this was transmitted by Lunar Orbiter 1 in 1966. Earthrise, right? First image of what appears to be an Earthrise, because of what Gaza was talking about, that the rotation of the moon is synchronized with its orbit. If you're standing somewhere on the moon, right, with a direct line of sight to the Earth, the position of the Earth is not going to change. It's going to change a little bit, right? Because as you saw in that image sequence, the moon does wobble a little, and that's because of gravitational effects, and because it's not a perfect sphere. But the Earth is not rotating with respect to, the moon is not rotating with respect to the Earth. So that means that such a thing as an Earthrise is a misnomer. What's happening is that the astronauts are, of course, in the spacecraft orbiting the moon. So as they orbit, the Earth appears to rise, okay? But if you were on the moon, you would actually not see the Earth rising. You would actually see it static or close to. One of the first photographs of the first footprints on the moon, of course, by Apollo 11 astronauts. While doing this research, it's interesting that because Neil Armstrong was taking the pictures, most of the pictures of the first man on the moon are of Buzz Aldrin and not of Neil Armstrong. So there are just a few, and just recently they found one. There was a camera at the top of the lunar lander and photographed Neil's face. So the reflection is not there, and it's like one of the first. And I found this photograph where he's actually handed that picture, and he seemed to be pleased. But most pictures are of Buzz Aldrin. First Terra Luna telephone call, right? So of course when Nixon called and talked to Neil Armstrong and Buzz Aldrin. And again, it's not necessarily that this is one of the first images of Earth, but it's definitely a very iconic image of Earth from space by Apollo 17 astronauts, which was basically the last mission to the moon. And it's the first one that shows the South Polar ice cap, so you can see at the bottom of the image. First photograph, and well, yeah, you can see it by the word Earth. You see the moon. First photograph of the Earth and the moon as spheres, right? Because in the previous pictures you could see the lunar landscape, but not as a sphere. And so this was taken by Voyager 1 on its mission to the outer planets, right, to the gas giants in 1977. And then, this one I selected just because this black and white photography, it's so elegant. It looks very, very classy. And there's a glow to them that really makes them very, very special. So they're just absolutely beautiful. Panoramas, so we can see many, many stitched photographs showing the magnificent desolation, as Buzz Aldrin put it, when he stepped outside of the spacecraft. So these were taken obviously by the astronauts, I guess in a manual way, and then they were stitched together. Yeah, so this is, right, they look very, very cinematic, right? They're just stitched panoramas, but then in the film, you bet that I will be showing many of these, and then showing them very, very slowly. I always edit my films to go with the tone and the tempo of the music, but yeah, it's just like having actual footage. Not to mention that Apollo footage has been re-released and reprocessed, and it looks great. And again, because I had to very, very choosy of what I showed, I didn't bring in any of that footage, but it's also amazing footage. And this one, I just thought it was, I don't know, I simply like this image, the fact that you're looking down and you see, the command and service module from the other module where the orbiter, basically, right? So you had two astronauts landing and walking on the moon, and then the other one in the orbiter. So here they basically are approaching, it's a rendezvous between the modules. And then this one I chose because it's basically very, very similar to what I'm doing these days, which is photographing the moon from different places on Earth. So I thought this was just a beautiful, beautiful photograph of one of the Saturn V rockets and the moon. And then this one, because of course it's related to Chicago. You know what, actually, no, I'm sorry. I thought, oh wow, yeah, this is the Chicago one. No, this is the New York one. The Chicago one is not as exciting because it's photographed from the back of the parade, and they are, at a distance. So unfortunately, it's not as good as this one. This one was New York. Okay, and then another component, and by the way, I'll end my talk by showing you examples of how these works look like when they're edited to music. So I'm going to show you one about stars and the starry night, and then I'm going to play Mars for you. And one of the things I use are animations produced by NASA to basically to convey to the public what is it that these missions are doing. So I thought that this one in particular of LRO, that is Lunar Reconnaissance Orbiter, and I should say that the Adler Planetarium is a partner in that mission. We are the lead educational institution. So here you see it. Lunar Reconnaissance Orbiter, by the way, it's tied to the fact that we want to go back to the moon. So it's mapping the surface of the moon to a resolution of about 0.8 meters per pixel. Very, very high resolution. And it has a laser altimeter that's basically not only photographing, but it's making a topographic map. Actually, some of the things that we showed before with the far side and the near side, that was taken by an instrument. It's called LOLA. It's a laser altimeter on board. Look at that. I think it's just the way, the camera movement, it's just that it looks very, very cinematic. So these are kind of some of the animations that I'll be using in the film. So basically, I research material for months. And once I'm comfortable with the amount of material that I have, I start, listening to the music and start trying to tell a story visually. And instead of just showing things at random, try to, follow a story. Okay, and then so let me go through some of my own photography that I, that now, of course, every time regardless of where I am, I'm photographing the moon. So this is, of course, showing the moon with some, Chicago architecture. Right, Millennium Park. North Avenue Beach. Navy Pier, right? So here, so again, it's the whole thing about art and science. So what I like about this photography, actually, I'll show you an example that better illustrates that, is that then you can communicate science through the photography, right? You use the photography as a hook to get people's attention, and then you can actually explain concepts. Here, this one, unfortunately, looks kind of dark here, but you see that, so that's the Adler Planetarium, and that's Monroe Harbor, and we see that, of course, as the moon rises, it goes through a shorter path of the atmosphere. So at the beginning, we have a lot of scattering. Blue light gets scattered more easily, so it gets scattered out of the way, and what remains is red, right? And there are a lot of dust particles in the atmosphere, but as it goes up, you're starting to see the moon through a shorter path, so there's less scattering. So that's why it goes from red and orange to yellow, and eventually just looks, almost white, right? The other thing that you can see, actually, if you were to study it carefully, you would see that it gets distorted because its atmosphere is looking like a lens, but the higher it is, the less the distortion. And also that when people say, oh, did you see the moon rising today? It looked enormous, it was huge. That's actually happening in the brain. It's an optical illusion. Unfortunately, if you grab your camera, take a picture of it, then take a picture of it when it's high in the sky, it's the same size. It's right, unfortunately, it's a trick. And this demonstrates it. It has the same width. So it would look huge to the brain. It would look huge, in the first sequence, but then by the time as it goes up, it looks, it looks less impressive. And that's because we're comparing the moon to things that are underground, but when it's high in the sky, there's nothing to compare it to. So it's just basically, in the almost empty sky, right? That's the dome of the Adler and moon rising. The moon at the British Columbia Parliament in Canada. This is in Santa Fe. So, and again, this is also icicles, and you see the drops falling. You see the icicles melting. So the idea again is to put the moon in also in a cultural context and show. I'll also show some time-lapse sequences where it's basically showing the moon bathing different landscapes on Earth. So that's all San Juan in Puerto Rico. Also, show that basically romantic aspect of the moon, not only the scientific. And here are a few observatory pictures. This is in South Africa. This is a fisheye view looking up. So I love this piece because it looks very abstract, right? So you look at it, it's like, what is going on here? And then there's a lot of science that you can explain. So it's a fisheye view looking up. So you see telescopes on Mauna Kea, Hawaii, on the Big Island. You see some, big domes. You see the red portion. It's basically a laser that it's monitoring what the atmosphere is doing, and then they make corrections in the telescope and get sharper images. And then, of course, you get the moon being eclipsed by this telescope called Gemini North, and then it reemerges. And then, of course, you see the rotation of the Earth, so the sky appears to rotate. You see Polaris on the other end. That's the Canada-France-Hawaii telescope. So again, it's images that are very visually appealing, and then you can explain a lot of concepts. Here you see Scorpius. It's right above, and the moon. This is from Chile. This is also from Santa Fe, just a very small crescent-shaped moon. And there's something called Earthshine that it's hard to see here with this projection, but the dark side of the moon, you can actually see it. And that's because Earth is reflecting light hitting that part, and you can actually see that. So it's not completely dark. This is from Chile. You see a moon just peeking through, a break in the clouds. Again, even this was the morning after. So here, of course, the moon is approaching new moon, so that's why it's looking thinner and thinner. Here you can almost, and that's why, it's related to what Gaza was saying, because, during the day, the contrast is so low that it's hard to miss the moon, but there you see it. But again, it's a little bit challenging to photograph, and again, it's just a matter of contrast. Now, this is close to sunset, right? Sunlight is hitting those clouds, see, not the ones in the bottom part, but then, now we get enough contrast that we notice the moon. Same thing here. This is my attempt to emulate an Ansel Adams photograph. Very, very high contrast. This is from Old San Juan, from the same session. And then I love photographing through windows, on flights. So here you see a crescent shape moon. This is close to sunset. This was coming from San Juan on that same trip back to Chicago. So that was kind of challenging. I had to take a lot of pictures just to get one sharp because, of course, the motion of the plane, and of course it's high magnification, so it's kind of tricky. And then here, this is the same flight. So of course it's getting darker. Now it's hard for me to expose to for the crater, so I'm overexposing the moon in order to get the rest of the scene. But you see that, sun is setting, obviously. This is really dark. It's just that with these new cameras, I'm able to take these pictures, with a decent amount of noise. Okay, and then of course that's after sunset. Okay, so let me show you some time-lapse photography. This is from Portugal. This is on a beach. This church is right there on the shore. And again, it's hard to see because of the contrast here, and also because I haven't processed these images. But you can see the tide going, you can see the surf. That's the Atlantic Ocean, and it's set right at that moment. So with more processing, we'll be able to see more. This is in Bath, England. This is a moonrise. So some of these are, my intention was to, of course, photograph the moon. Sometimes I just noticed the moon. Like here, I was at the in the hotel room, and I just noticed the moon rising, so I just quickly grabbed it and made this sequence. Stonehenge. Sometimes, of course, the weather doesn't cooperate much, so here we had a lot of clouds. But on the other hand, it's all about moonlight, right? Moonlight is what's illuminating the scene. And again, related to what Gaza was mentioning about things being scheduled with the phases of the moon. In this case, this was, I think, the day before full moon. And this was just a few months ago. Okay, a sequence of the moon rising with Navy Pier. So of course, this is happening very quickly. These photographs are separated by about maybe five seconds. So it's like every 5 seconds a photograph, and then I make the movies. That's because of the wind. You saw that motion. It's because, of course, it's usually windy here. Okay. Let's see what else. So the Adler, and again here you can talk about time scales, right? And time perception. It's almost impossible to see the moon rotate, moving across the sky because it's happening slowly. But then if you speed things up, then you can actually see that. But then of course everything else is sped up. So just to talk about time perception using time-lapse photography, it's a very effective way of talking about that. And then, of course, it's very difficult. The light conditions are changing constantly. So whenever you see a cut, it's not because I'm just being, smart, trying to make a nicely edited film. It's because it's too dark, so I have to change the settings. So I cut to another scene and then go back to that. See, so here it reaches a point where it's too dark, so I have to cut to, to another scene, and sometimes I return to it. This is from Old San Juan. And it's good to have clouds, because otherwise you just see the moon, rising. If you don't have anything else, no other moving elements, it could be a little bit dull. But when you have other elements, then, this whole thing about time perception becomes more interesting. Okay, and so to wrap things up, I want to show you two finished products. Sidereal Motion is the first work that has been the result of my collaboration with Tom Bailey from Thompson Twins. And it's all time-lapse photography accompanied by music that he composed for the film. So it's like the other way around. If I work with Holst, Holst is like not around to make changes for me. So I just have, dead composers are not good collaborators. So I basically have to, okay, Gustav, what is it? Is this what you have for me? Good. But when it comes to working with a living composer, of course, you can go back and forth. And so I want to show you the end. It's 4 movements, just like a symphony with different tempos. And I want to show you the last movement. And actually, it features the moon as well. So I might use some of that footage in Moonrise, which, by the way, it's the title of the film. So here I'm going to, this is KV265, who's sponsoring the production of the film and so on, and coordinating our concerts. Like Paul said, we'll have one at the Adler. But what I want to do is I want to fast forward. All this is time-lapse photography. That is, every single frame is a photograph. So I want to go to here. And like I said, whenever you see something that is nicely illuminated and then it gets dark, that's the moon setting, okay? Not this, we're not taken during the day. And this is Tom's music. That's the moon. And this is, by the way, in Chile, in the Atacama Desert. Thanks. And then my one-way collaboration with Gustav Holst. Thank you.
Well, I want to thank Gaza for his excellent science overview of the moon, and Jose Francisco for tantalizing us with how you can marry art and science into what I'm sure will be a very inspiring moonrise performance later this year. So we have some time for questions. If anybody has any, I'll be glad to direct them to one of the two. John.
I think I recall a story I heard when I was in grade school about Christopher Columbus using a lunar eclipse to impress the local folks when he went to West Indies. What was that?
As I mentioned, to sort of understand the cycles, the lunar eclipses come in cycles, Saros cycles they're called, and these were actually known as far back as the Babylonian times. But you have to have sort of a grasp of mathematical patterns, have a long history of observing solar and lunar eclipses. But once you sort of catch on to these cycles, predicting when you're going to have another eclipse of the moon isn't so difficult. But if you don't have a long history of observing and you don't have the mathematical underpinnings, then a eclipse of the moon is something really sort of frightening and scary. I mean, is the moon ever even going to come back? And so if Christopher Columbus sort of had the ace up his sleeve, that he knew when one would occur. And so he could use it to sort of impress that, well, you better help me, or, the moon may not come back.
Right. I'll ask my gods to make it disappear, and that's what he said. So when they saw the eclipse, starting to take place, he said, okay, what do you need? So yeah, it is true.
Other questions? Yes.
This is for Jose. I'm curious to know what came first, your interest in science or your interest in art?
In science, actually it goes back to the moon. I found this book about the first man on the moon that my dad owned. I was in 3rd grade, and I opened it and I saw all the illustrations and paintings and photographs, and ever since I got interested in science. And then other things that I considered as a career were photography and then music, and then many years later I found myself combining them all in my work without never being like my master plan, right? It was never my intention, but it was interesting to realize that all the things that I liked and considered before I was combining into these works. Yes, very lucky.
Yes, sir.
Last Friday, the Chicago Symphony did one of the Charlie Chaplin movies for the score. So I wonder if you could line up the Chicago Symphony.
Right. Yeah, I have a long list of projects, either music or particular works that I would like to use, or particular concepts, and that's the idea that through this new organization, KB265, we'll be able to turn these things into reality, and not only in the production aspect, but also coordinating with all these orchestras around the world. And of course, CSO would be. At this point, we have collaborated many times with the Chicago Sinfonietta. We haven't collaborated with the CSO yet, but hopefully, that will change at some point.
Yes, ma'am.
For Gaza, the reflection from the moon being right there, the surface of the moon is only, it seems, 1 to 4 kilometers difference. What is the difference between the volcanic dark portions that causes such a great difference in reflection?
All right, so why are the dark portions of the moon, the mare, so much darker? Basically, it's just as the chemical structure. The dark areas are this basaltic lava that comes out, and it's the crystalline structure is usually smoother. Another difference is that the Highlands has been processed a lot more. There have been a lot more craters. And so it's been pulverized much more strongly. And when you pulverize things, and you've got this thick dust coating layer, it tends to sort of lighten materials. And so the difference is, significant. It's sort of exaggerated, enhanced by the fact that you're looking at this against a completely dark background as well. But there's distinct chemical differences between the Highlands and the Mare. Basically, the Highlands are not a volcanic material, and the Mare are. And one of the forms of basalt, obsidian, for example, is a basalt. It's sort of more glassy material. It's very dark.
In the back.
The difference between the topography of the here and the far side, is that because the new side gets more collisions or just more recent collisions?
That's not entirely settled, but it may also have to do with the pattern, the distribution of the mass. The moon is in a synchronous orbit. The rotation and the orbit are synchronized, so you always see one side. And typically what that happens, basically the moon exerts tides on the Earth, but the Earth exerts tides on the moon. In fact, the tides of the Earth on the moon are 80 times larger because the mass of the Earth is 80 times larger. And so that tends to slow down the rotation of the moon and lock it in. And the lock, it's basically, if the moon isn't completely spherical, then the side that'll sort of break the symmetry. If it was totally spherical, it just keeps it could spin, and it would sort of just stop at some random location. But so that discrepancy, the fact that it's very different meant that you sort of ended up oriented. I think that there's larger concentration of mass on the near side. It's just sort of a asymmetry.
Wait a minute.
Are there plans to go back to the moon anytime soon, or we're still thinking about leaving the moon and going to Mars?
So there are plans. Whether they're going to be implemented is another matter. So the whole constellation program that NASA put together, which was sort of the Apollo on steroids, is a very reasonable way of going back to the moon. It's basically doing what we know how to do, doing it better. But unfortunately, it's also an expensive thing to do. And some people are asking questions of, why bother go to the moon? Why not go straight to Mars? You can make mission plans to go to Mars just perfectly fine. What I tried to sketch out was the moon is interesting in and of itself, and it's sort of a local source of raw materials. Of course, you can also say, why not go to a near-Earth asteroid? That also is fairly easy to do, and you could even more easily get materials out. So there's sort of cost-benefit, and exactly what we'll do first, I'm not sure. Right now, funding for Constellation is basically in limbo with the current sort of budget issues in Washington.
Okay, I think we have time for maybe one or two more questions. Seeing none? Oh, wait, okay. Yes.
So yeah, the moon is moving further away from the Earth, and that's actually a tidal effect. As the Earth is actually slowing down. The moon is slowing down the Earth's rotation because of the tidal bulge of the moon of the Earth lags its rotation, so it tends to sort of torque it and slow it down. And that angular momentum that's spinning has to go somewhere. And what it ends up doing is it gets pumped into the moon, and the moon is slowly moving out. And slowly the tidal forces will go down. When the moon was first formed, it was much closer to the Earth, and the tides were tremendous. I mean, an 8-meter high tide would have been nothing. You'd have had that in any ocean, any seafront property. You had tides of hundreds of meters back when the moon was first formed, but rapidly it moved out.
And as a result, then the Earth is going to have a synchronous rotation with respect to the moon. So the Earth is going to slow down so much that then at a certain point, just like I was talking from the perspective of the moon, basically the Earth is going to be rotating, spinning at the same rate as the moon is going around us. So that means that only one hemisphere of the Earth is going to be able to see the moon, because they're going to be completely locked.
So our days are getting slowly longer. That's why every year or two or three, we add a leap second on New Year's Day. Yeah, just to keep our clocks in synchronization with the Earth's rotation. Yes?
What kind of time frame are we talking about for this?
A very long time.
Long time.
By the time the locking occurs, that's very long. The Earth's rotation earlier was, I mean, we're talking about sort of 20 hours, 12 hours, etc. By the time it gets locked, the sun will probably have expanded and burnt up the Earth anyway. So it's maybe academic interest, but.
And before that happens, we're going to collide with the Andromeda Galaxy.
Right.
Are there any other questions? If not, then let's thank our speakers again this evening.